Hello, my name is Ralph Maltby, and welcome to the GolfWorks Golf Club Design Facility. The entire facility is made up of 3 areas: the golf club design studio that you're sitting in right here, the machine shop, and the grinding and polishing room. In the studio, I have a bunch of very interesting and powerful tools that I use in the design of golf clubs, from CAD/CAM systems to robotic putters to moment of inertia machines to gauges to check center of gravity, and a lot of other very interesting things that we'll look at later on. In the machine shop area, we use very sophisticated CNC equipment to machine out prototypes and master models and make up various parts, and I even use it for designing tools. In the grinding and polishing area, we can put virtually any finish on a golf club, from vibratory finish to high polish to satin finish, you name it. And we also do a lot of blending on the prototypes and looking at different aspects of how the club will look in the playing position. So all three of these facilities, if you will, put together, comprise the entire golf club design area. It's very interesting. I love working in this place. I'm generally in here all by myself, and it's one of the most exciting things that I do. And the ultimate reward is when you finally bring a new golf club design to market. Golf club design has come a long way, and in the future will continue to even go further. In the studio here, I have clubs that represent the era of the 1950s, the 60s, the 70s, the 80s, the 90s, and into the year 2000. There are many different types and styles, everything from the mild to the wacky. And I've done some of the wacky stuff myself in playing around and trying to come up with new designs. But I use this room here with these thousands of golf club heads that are in it, from putters to irons to driving clubs to metalwoods to woodwoods, to review the past, see where we're at currently, and get ideas for the future. This is a good way to start off with a new design concept. And the first thing I do, because people always say, well, Ralph, how do you come up with a new idea? There's a lot of inspiration for a new idea. Someone at work can suggest an idea. You can see something that says, you know, I know how I could make that better. And then there's just a plain inspiration where you come up with something that may be wild and wacky or just a brand new design, and testing then may show that some new concept is going to work out better, and it's time to sit down and design that in that direction, make a prototype, go out and test it and see how this really works. So what I do is my first step, and in the past, before the computer era, the whole step was sitting down and making drawings and sketches and starting off that way and taking clay models and building them up in that direction. And that's how I started in doing designs, and a lot of them in the 70s and 80s were done that way. But now I sit down and I still get an idea and I sketch it out on a piece of paper. I have a very powerful CAD/CAM system sitting here behind me. It's a TechSoft system. I use SolidWorks in it, 3D modeling. You can do a ton of designing on it. But I still like to sit down at this desk, do a face outline and the blade shape that I'd like if it's an iron we're designing. I like to look at a scoring line pattern. I like to determine the blade length. There's some very important measurements in doing an iron club design, and we'll just focus for a moment on iron clubs. We'll get into woods and putters and a lot of that later. But it's very important in iron club design to understand some relationships that as a designer that you must keep in mind. And besides these relationships of dimensions, you always have to be designing for the type of playability you're after. And that playability can be determined a lot by where you locate the center of gravity. Where's the center of gravity in relation to the center line of the hosel? How long is the blade length? That leads us into what moment of inertia does this club have, or what moment of inertia am I looking for? And we'll talk a little bit later on center of gravity and moment of inertia and get a little more specific as to how they relate to the playability factors throughout different designs of clubs. But right now it's important to know that we start off with our sketch. I start off with the sketch that way. I don't know how some of the other people do it. Then I go into the computer and go into the TechSoft CAD/CAM system. I go into CAD first, which is computer-aided design, and that's a drawing program. And I start putting in the radiuses, and I start manipulating things, and I start looking at the type of cavity I want on the back of the iron. I've done the blade shape. I work on my scoring line presentation. What type of sole? How much bounce angle will I put in? It's easy to start it off. I usually start with a 5-iron. I know I'm going to establish a certain loft angle and a certain lie angle. I may change those later, because if I have a long head shape, I may have to go with a slightly more upright lie because they'll tend to flatten more coming into impact. If I go with a real low center of gravity, the ball will tend to fly higher, so I may want to decrease the loft a little bit. That'll all be determined in testing. So I work in my CAD system and I work up the designs, the front, the back. I work it into solids. I rotate it. I get a look at it. My next step is to figure out how to machine this thing. And out in the machine shop, I've got a CNC mill, which is computer numerically controlled. And on that mill, I have 58 tools that I've defined. And of these 58 tools, there's everything from hogging cutters that remove material fast, special aluminum cutters, steel cutters. I've got die sinkers cutters that have relief angles on them. I have little radius cutters. I have engraving tools. I even have a digitizer set up, which doesn't cut anything, but it can take patterns for me, and I can put those into the computer. So what I'll do is I'll get into the machining aspect, decide what tools I'm going to use. In regards to face lines, I know I'm going in with some engraving tools. So I'll use an engraving tool, a 30-degree angle engraving tool. I'll set it at the proper depth because this is going to be a prototype I'm building. I'm not building a master model at this point. I want to build the exact golf club that we're going to come out with. And if that doesn't work in testing, then I'm going to keep modifying it and modifying it. But I have my program in the computer that I can keep adjusting and adjusting and adjusting. Just like in Microsoft Word, when you do your save as, I keep saving as and changing it and saving as and changing it. So my goal is to build this model, define all my tools, and get it cut out. And then I'll go on to the polishing and grinding machines and do a little bit of blending here and a little bit of blending there because I want to see what kind of look I have. We'll take that design off and do some testing on it and see what people think when they go out and actually hit it. Usually, probably in 50 or 60% of the cases, I'll come back and make some modifications. It may have performed just fine, but there may be a little bit of a look at the toe you wanted to change. Or there may be a comment that, oh, well, it doesn't look like it has enough offset. I'd like just a little bit more. Again, it depends on the type of iron you're designing. Are you going for super game improvement? Are you going for just a game improvement, heel, toe, sole weighted iron? You're going for conventional that has more playability features but looks far more conventional than some of the clubs that are out today? Or are you going for the classic old-fashioned look? And again, we'll talk some more about that as we get going into this presentation. I'll use actual examples to compare old to new and tell you why and show you how I have evolved the classic look into what I think is the more classic look in using modern technology. And some of that, just as a little bit of an insight into it, is shortening the real long hosels of the 50s and 60s that sat way up in the air. I brought those down a little, but still retaining the classic shape. Why? Because the club has additional playability built into it by doing that. And I'm always looking to control the center of gravity where I want it. And again, the design dictates that. I mean, if I'm going for super flat out, super game improvement irons, I'll work to get the center of gravity as low as I can. I'll work for a high moment of inertia. I'll do a great large C dimension, which you'll learn about later what the C dimension is, a very important characteristic of playability in an iron. But we'll get into all of that, and all I'm trying to do here is give you sort of a overview, if you will, on how we use the sketching apparatus, get into the CAD system, go into CAM, which is computer-aided manufacture or machining, whatever you want to say, then out to the mill, into the polishing and blending, stick the shaft in it that you want, set it up with a grip, frequency check it, check the lofts and the lies, they're already perfect specifications, but make sure that everything is right, and then go out with control clubs and a group of people and let them hit the control clubs, their own clubs, and then let them hit the new prototype clubs and give you feedback. One of the big differences in designing a metal wood is that I cannot make the prototype in this shop. I can make the master model in this shop and get the exact shape I want, but I can't make it playable because I need hollow iron technology. It needs to be cast or forged. It needs to be made in the material that it's going to be tested in and also heat treated properly at the foundry. So what I do is this. I use the same procedure I use on irons. I start off with my sketches. I get into CAD/CAM back here. I design up the shape that I want in the wood or hollow iron. This applies to all hollow clubs, not solid clubs. So I get the shape that I want, and then what I do is I take this solid block of aluminum, I set it up in the mill, and I machine out the prototype. And actually, it's more of a master model than a prototype because it's slightly oversized to allow for shrinkage that occurs during the investment cast process. If it's going to be forged, the oversized aspect of it isn't quite as important, but when it's cast, it's very important. So what I get out of this is a solid aluminum model like this that I made a number of years back. This is an older head style. It's a 220cc club. But it's solid aluminum, and obviously it's not playable because it's way too heavy to go out and hit. So when I machine it, I get the outside and everything exactly the way I want it, send this head off to the foundry, and let the foundry make up a mold. The foundry then casts the head in the proper material, heat treats it properly, but what I ask the foundry to do is not put in any additional weight. In other words, whatever shell thickness they need, make the entire club the same shell thickness. That way I get a head back that's approximately 15 to 25, sometimes 30 grams, depending on the size of the head, light. And in that manner, I can take the heads when I get them, and I get maybe 5 or 10 prototype heads. I'll put lead tape on the soles, I'll lead tape on the toes, I'll do some forward weighting, backward weighting, again, depending on the size of the head and the type of design that I'm looking for. I'll get it all up to weight. I'll do the centers of gravities on the prototype heads. I'll put them on the moment of inertia machine and check the moment of inertia. Then I'll assemble them all up with the identical shafts and grips and go out and do some player testing. The player testing will then generally determine which way the club will perform the best. We can even take the clubs down to true temper and use both of their indoor or their outdoor hitting machines and also get other lab data in that manner. So then the club goes back to the foundry. And I tell the foundry where I would like the weight put. So they build me one more prototype, the weight is put inside the head, and in this manner we can test it just before we go to the final design and the final set of molds for the club that we're going to come out to market with. So they send them back, we do the testing, and just verify that everything is just fine. In the case of hollow irons, it's the same deal. Here's the Sand Slider, which came out in the 2001 GolfWorks catalog. This is made out of this same aluminum block right here that this wood head was made out of. This is solid aluminum. I've engraved the face lines. I sent this off. I made it slightly oversized because this is investment cast in stainless steel and hollow. And I got back the hollow shells. I experimented with weight very low in the sole, out toward the toe, and ended up with the exact design that I wanted. So anything that's hollow, we start with this solid aluminum block, go ahead and build sort of a master model, get the foundry to go ahead and send us in shells, and go from there until we get the playability just right. It's a lot longer process than doing a prototype iron, since I can do all that right in the shop here and go out and do the testing as I mentioned. But it's a longer process, but it's very interesting. And again, the excitement always comes when the final product comes to market and you see it all done and paint filled and polished properly. One of the first things we really need to talk about is center of gravity. Sounds technical, but it really isn't. It's a rather simple concept, and once you have that, you'll understand a lot about golf club design. This applies to putters, woods, irons. And let me show you a little example here. I'm going to take this board. This board has a bunch of lines on it. Well, if I take my finger and I balance this board on my finger right there, and then I draw a vertical line where it balanced, and then I rotate the board and I balance it right there, and I get it balancing just perfect, and I can get right to the center if I took my time, and then I draw a vertical line right up from that balance point. I go to this point and I balance it again, draw a vertical line, go to the center, go to anywhere I want that I can get this thing to balance, and anywhere I draw a vertical line, guess what? They all intersect right in the middle of the board. That's this board's center of gravity. But that's its center of gravity in that particular plane. Now if we turn the board sideways, we've got a certain thickness, and this happens to be basically 1/2 of an inch thick. So logic would tell you, since this is somewhat of a symmetrical object, that the center of gravity is going to be 1/4 inch in, 1/2 the width of this board. So at this point, buried into this board 1/4 of an inch is the center of gravity. The next example I want to show you that helps in understanding this is taking a golf ball. And we take a ball, and let's assume this one has 432 dimples. I have no clue how many it has. But let's say that I balance this golf ball right here on every one of its dimples. I balance it on that one. I balance it on that one. I draw a vertical line straight up through every balance point. Remember, Center of gravity in any object is being acted on, and it causes it to balance because of the Earth's center of gravity. Everything got gravity and wants to go down, so there's a balance point where it won't fall over, and that's what we're doing. We're defining this in relation to the Earth's center of gravity. So if I balance this on every single dimple and draw a vertical line, guess where they all intersect? Obviously, right in the middle of the ball. So there's a dot inside this ball right at its dead center. Hopefully it's at the center of the ball, and most of them are. And that's the ball's center of gravity. It's a symmetrical object. Very easy to determine center of gravity in a symmetrical object. It's the non-symmetrical objects, and then it's non-symmetrical objects that you attach to other items that have their own centers of gravity, shafts, grips, that cause a completely different animal. So let's move on from here and do this. The next thing we're going to do is we want to find out the center of gravity of this iron head. And for the sake of this discussion, we're going to start off and we're just going to find it out in one plane. So I take our little center of gravity machine right here, and I set it up. This device has a marking pen, a permanent marker in the center, which I've set up that goes up through a little teeny hole in the center of this. So I'm going to take this iron, and we're going to balance this iron on this device, and then we're going to push the pen up through it, and we're going to mark its center of gravity. And I'm getting close here. There'll be a point where she balances, and I just about got it right there. And there. Center of gravity sees a very minute point. There we go, got it right there. Now I put my finger down on it to hold it at that spot where I have it balancing. I bring the pen up through the middle and I twist it. Then I take the club off of that, and I've got a little mark right in the center of the face, which is the center of gravity in this plane from toe to heel and up and down the face. So I have a measurement. If I want to do a rough measurement, and this is not how you precisely measure center of gravity because it doesn't take into account the sole radius or the bounce that's built into a club, but if I want a quick measurement, I'm going to take my vernier calipers right here, and I'm going to just put it on the bottom of the club, and I'm going to measure up the face to that point, and I'm going to read it, and it says it's up 750 thousandths, which just happens to be 3/4 of an inch. The other thing I can do, and every golf club that I design it so that there's a center line in the face. The scoring lines are about that center line, and then I also establish the sole radius to be about that center line of the face. So everything that I do is a balanced design so that when you do a center of gravity and you go ahead and measure from the length of the scoring lines and divide it by 2 to find the face center line, then you'll see where the center of gravity's at. And on all Maltby designs or any clubs I design, I make the center of gravity either on that center line or purposely toward the toe. And the reason you do not go into the heel, and there's a big myth involved in this heel center of gravity thing, and don't believe anybody that tells you that better players prefer the center of gravity in the heel. You don't want to do that. Where that all came from is back in the old days, 50s, 60s, the touring professionals hit the ball always on the center of gravity. I mean, they're off a little bit here and there, they're human. But what they do is they end up with a wear spot on their iron. And this wear spot causes a little round circle. And back on all the old clubs in the 50s and 60s, and a lot of them into the 70s and some into the 80s, they would end up with this wear spot toward the heel. Therefore, some club designers would conclude that, oh shoot, I think the center of gravity should be always toward the heel because that's where the good players hit it. Wrong. Good players hit it in the heel on the older designs because that's where the center of gravity was. Any person that hits a lot of balls and hits them consistently will get a wear spot, and where the club feels the most solid, it's going to be hitting basically very, very close to the club head center of gravity, particularly in this toe to heel direction. So you don't want center of gravity from the face center line toward the heel. That's just a no-no in club design. So the next thing that I want to do right here is take a finished club. Here's the Maltby Logic Pro Forge. This is a good example. Okay, we know that we can find a center of gravity somewhere in the face. So this one has one somewhere, but we know it's inside the head. Well, here we have a total golf club that I'm holding in my hands. Total meaning we've got a shaft and we've got a grip on it. Well, the whole golf club as one unit's going to have a different center of gravity than just where the head's at. In other words, if I take this golf club and I balance it on my finger, just like that, now I've got a plane that if I draw a straight line down and up through this, I'm going to know that the center of gravity on the whole golf club is on that plane. And then if I go ahead and I stand it up on its sole like this, and I get it to where I can balance it and draw that line straight up, those lines are going to intersect. I can do it on the grip end. Get a thing on the grip, you know, and I can draw a straight line up from that and find it. Well, what'll happen is, since this club balanced about right there, the center of gravity for the total golf club is not inside the golf club. It's sitting about right there. There's its center of gravity. Well, you can't hit the ball with that center of gravity, can you? You hit the ball with the club head. And one of the things that makes a golf club unique as an implement in striking a ball is the fact that the head acts independently on its own at impact. It acts about its own center of gravity. It's the bulk of the mass. It's all the mass that's around that center of gravity. It's its moment of inertia and all these other things, which we could touch on a little bit later on some of the other points. But now I go back to the total club. So let me throw this in while we're doing our center of gravity discussion. And that is, you say, oh, did Ralph just say that the shaft is not important? The shaft is obviously extremely important. And shafts, as you know, have all those characteristics. You know, some bend down here, some bend up here, some are mid-deflected and bend in the middle. They're stiff, they're medium, they're flexible, they're ladies, double ladies, what have you. They have all these characteristics. So what does the shaft do? It takes your swing, however that is. I mean, you could be an accelerator, accelerating at an accelerating rate into impact. You can have this steep angle of attack. You can drive the center of gravity of the head deeper under the ball. You can have a later wrist release. All these things cause the shaft to torque and bend slightly differently than the next golfer hitting a shot. So we all know that we like certain golf shafts, the most of us, better than other golf shafts. So what makes a golf shaft that you like, I mean, a golf shaft that you really like, that hits the ball well and gives you solid feel, is simply this. That particular shaft that you've selected through its certain length, you've stuck a certain weight head on it, and this is all what? We're getting kind of toward frequency matching when you start talking all these elements. But frequency matching comes down to what happens when you hit the golf ball. And when you hit the golf ball with this total assembled club, that shaft does nothing more than bring this club head into impact with the golf ball in the same position every time. If you put the same swing on it, and if you vary your swing, it'll vary that. But the point is, with your particular swing, you want that golf shaft to do all its twisting, bending, whatever it does, and bring this club head into the same impact point time and time again. That's what the golf shaft does. The head, center of gravity, and moment of inertia act on their own at impact. So you definitely want to impact the ball on the club head center of gravity, otherwise you get twisting and all kinds of things happen. But the worst thing is you lose distance and you get an unsolid feel, and a lot of the times you get poor directional control. So consider that when you're looking at the total golf club. And I like to refer to that, and there's a lot more elements of it because you do dynamic club fitting, you put all these parts together, you check the frequency, but I like to call it dynamic playability. And that is doing everything that you can for the golf clubs that you're going to play with, that you can make them the most solid and the straightest hitting clubs with the trajectory that you like that you possibly can get. And that's doing a little experimenting with golf shafts. It's installing them properly, finding your right length, getting your head weight, getting all these things right. But just remember the term dynamic playability. I really like that term because it locks everything in and says that you need to really analyze everything about your swing and about all the parts that you're using in a golf club. Moment of inertia is a term we've all heard. We've seen it in advertising copy. I've written about it in the Maltby Club line because we utilize it here in the Golf Club Design Studio. The key thing is understanding what moment of inertia is. So let me try to explain it. If we have a barbell, and let's say it's a 36-inch long shaft in this barbell, and we have two 5-pound weights on that barbell, we slide them into the center of the barbell, and I can pick it up, and I can rotate it just like this, because moment of inertia is also referred to as rotational inertia. So I'm rotating, and it's pretty simple to rotate and make it just kind of pivot around like this. If however, I take those weights, the 5-pound weights, and I move them all the way out to the end of the 36-inch rod, and now I pick it up by the center, it's a lot tougher to rotate. Much more difficult. So that portion with the weights on the outside is said to have a very high moment of inertia, and when the weights are on the inside, that's a very low moment of inertia. To more fully understand moment of inertia, we'll actually check a couple clubs right here in the studio. Sitting in front of me is a Rockwell moment of inertia machine. Very sophisticated, very expensive machine, but you get invaluable data out of it. The unit that I have will take up to a 5-pound object, so a golf club is no problem, and it's also computer controlled. I have a software program in the computer. I control the entire machine from the computer, with the exception of taking heads off and putting other heads back on. So I can bring all my data in, I can analyze it, I can look at all the different units that it's measured in. What we're going to do is measure this golf club that's sitting on it right now in ounce inches squared. There are many other units that will give you an appropriate reading for moment of inertia. There's like kilograms per second squared, there's grams per slug for something else. There's a lot of them. I just like to use ounce inches squared, and I can also add per second on the end if I want to do it in those units. But these units seem to give me a nice base for how I'm analyzing the data. So sitting on the machine right now is a golf club. So let's go ahead and take its moment of inertia so you can see exactly how this sophisticated machine works. So I'll slip over here to the computer screen. I work the control pad right off of the computer screen. So right now it's telling me to move the lever to the right. So I'm going to let the computer tell it to move the lever to the right. And a little motor is running right now, and you see the club turning, and now it releases. And it's going back and forth. And this is your moment of inertia, rotational inertia. And what this machine is measuring is that golf club's resistance to start in the other direction. It winds it up, it lets it flop back and forth, and it knows how difficult it is to get it to go in the other direction. Just imagine if our barbell was sitting on the top of this. I mean, it'd take forever to get it to go in the other direction. So that's measuring moment of inertia, or its resistance to rotational inertia, if you will, or resistance to rotating. So we've done that, and we've got a reading, and I'm going to click and get it converted. And this is 11.28411 is the moment of inertia on this particular iron. So this is a very low moment of inertia iron. And I know that because I've done so many irons. Now what this club is an old 1969, I believe, Ben Hogan +1 forging. It has a relatively long hosel. It's a relatively short blade length. Basically muscle-backed, if you will. It doesn't have any cavities. It's got a pretty thin sole on the bottom, so they've left this section pretty thick. So what we have is a very low moment of inertia. We have a club with a very high center of gravity. Not very high, it's 0.830. But it's also 1/8 of an inch into the heel. Let me show you one other example. We won't take the moment on this club. Here's an old Tourney McGregor color chrome iron. It was very popular. It was played on the tour also for quite a few people. Well, look at this. I mean, there's probably one of the longest hosels you've ever seen, relatively short blade length, and this one's truly muscle-backed with the weight in the center. Another high center of gravity, way up into the heel area, and another very low moment of inertia iron. Here's our next example, and this is an interesting one. I have right here the old Acushnet AC-108 iron. And this iron came out in 1972, I believe, and they sold a lot of sets of this iron. This iron has a center of gravity that's at 0.970 up the face. It is way up the face, dangerously high, and into the heel by another 1/8 of an inch. It has a relatively long hosel, not super long, but it was one of the first irons ever to come out with tungsten heel and toe weights. And it was a great advertising thing, and tungsten really works in an iron if you put the weights in the correct location. On this one, look where they're at. Excellent for a beautifully high moment of inertia, heel and toe weighting, perfect, but they're very high up the face. And then they hollowed out all this area down here in the sole to further take the center of gravity higher up the face. So the design was all based around a high moment of inertia, but with a complete disregard for center of gravity. Moment of inertia and center of gravity are separate in a head, but they must be designed together in that head to make a club super playable. And moment of inertia is like good cholesterol and bad cholesterol. There's good moment of inertia and bad moment of inertia. And for those of you engineers out there, you're probably rolling your eyes right now, but here's my example. Bad moment of inertia is when you take the weight distribution into the heel and toe and you put it high up into the head. Bad moment of inertia is when you increase the moment of inertia by increasing the length of the hosel so that it resists twisting. Good moment of inertia is along the lines of this Logic Tech iron right here. You have an extremely long blade length. Let me just compare it with this AC-108. You have heel and toe weighting and sole weighting that's very low in the club, coupled again with the short hosel. So when I take this iron and I mount it, and incidentally, where I mount these, there's a hole drilled, and it's also on the center of gravity in this plane from face to back. I mark those spots and I drill it. This machine is so sophisticated that I can actually, if I miss the center of gravity a little bit, I can adjust it in the computer program and still read out the proper moment of inertia. So I'm going to put on the Maltby Logic Tech, which has no tungsten weights in it, but has a very high moment of inertia. As a matter of fact, the moment of inertia on this Titleist AC-108 and the Maltby Logic Tech are almost the same. Not quite. This is actually a little higher. But the center of gravity on the Maltby Logic Tech is at 0.720 inches up from the sole, and this is 0.970 inches. Very slight movements in the center of gravity make enormous distances in differences, not distances, although it can equate to distance, but enormous differences in how a club feels and how solid it is. This club right here that's sitting up on the moment of inertia machine was so easy to hit for a person that just can't strike the ball solid. This is a very, very difficult club to hit for a person that can't hit the ball solid because they must drive the center of gravity of this 5-iron down under the center of gravity of the golf ball. Very easy with this one. You can sweep with this one and do it. With this one, you better have a very sharp descending blow coming into impact to make that happen. So let's take the moment of inertia of this iron right here, and I've already kind of told you it's going to be a lot higher than that original Ben Hogan that we put on there, but it's going to be just a hair lower than the Titleist AC-108. And this brings up another good point, and there it goes, and it's flopping around right now. We'll get our reading. And I'll click it. 14.825. The original Ben Hogan Plus 1 iron was 11.284, and this is 14.825. So there's approximately, trust my math on this, approximately a 15 to 18% improvement in center of gravity location, but about a 25% improvement in moment of inertia, if those are right. I can figure those out. But the point is, you've just seen a demonstration of these big differences in moment of inertia on comparing these irons. Now, let's do something, it probably sounds great on the video, me sliding these irons around. Let's talk about putters for a second. We do irons on the machine, we do putters on the machine, we do wood clubs on the machine, and get the MOIs and compare them with different golf clubs. Wedges I don't worry about too much, although I do put each one up on there and get a reading off of it, but it's least important in a wedge shop because you have such a great amount of loft on a wedge that you don't impact the ball, you don't compress the ball very hard, there's not a lot of force there. So let's talk about putters for a moment. I have an old original John Ruder bullseye putter right here in my hand. And let me show you an example. We'll go back to our barbell example. I'm going to take this and hold this right here. And you can do this, and I'm not going to fudge this at all. I mean, this is the really, I can take this thing and look at how I can turn that. That's pretty quick. That's about as fast as I can do it. I'm rolling it in my fingers. Now I'm going to take a more modern putter, just a modern heel and toe weighted putter. This just happens to be a stainless model out of the Maltby line. And I'm going to take it and roll it in my fingers. That's as fast as I can make it go right there. You could do this and sit here all day, and you can't probably make it go any faster either. But you saw how quick the bullseye went. Now, I've put all of these types of putters on this machine, and you can see right there that you have almost double the moment of inertia on the heel and toe weighted putter against the bullseye type putter, which always leads me to the point of thinking that players like Tom Kite, who putted all those years with a bullseye, and I don't think he's putting with it right now in the senior tour, but he did for a while, would have putted and played a lot better had he had a heel and toe weighted putter. Heel and toe weighting is absolutely the way to go on a putter. Many mallets are heel and toe weighted. I mean, there's a ton of putters out there that are heel and toe weighted, but I basically am not a blade putter person. Here's another one. This is an original Arnold Palmer, quite a rare putter, and it's not heel and toe weighted, but it was a decent putter. But I wouldn't putt with this kind of putter today, and there's probably some good putters out there putting with it. What I would putt with, again, is heel and toe, and let me go up to kind of the ultimate in heel and toe weighting that's on the market currently. There's clubs out there like Carbide, and Carbide uses two big tungsten weights and a very light material in the middle. This is one of the highest moment of inertia, best heel and toe weighted putters on the market. There's one that's even slightly higher because I designed around this to go beyond it, and that is the Maltby Carbon Brass series, where what I do is I use a very lightweight carbon material and put two big, huge brass weights in the toe and the heel area, so the material in the center is lighter than even on the Carbide, and this has an even higher moment of inertia. So I feel like I've probably hit about the ultimate level of moment of inertia, and I did go one step farther. And a simple way, you're learning enough about a moment of inertia now to know that if I wanted to increase it right now, and I don't want to increase my weight beyond the 325 grams that this is, so I could stretch it out farther. So what I did is I came out with another model. And this model in carbon brass, all I did was lengthen the thing out. You know, some people love it, particularly the people that have had a lot of problems in putting, and the very good players absolutely probably hate it because it's long and ugly, but the thing works. The one that's the most popular, and the one, just for your information, that everybody in our company, and we have some very good players at the Golf Works, they all use this model right here. They've tried them all, and we had guys that used to putt with different putters on the market because, you know, that's kind of your pet club. They're all, including Ralph, putting with this model right here, this carbon brass model. Try it, you'll love it. So, back to our discussion. Moment of inertia is very important, but it's only important if it's done properly. Center of gravity in an iron club and a wood club are far more important than moment of inertia. But when you bring the both of them together and you do moment of inertia right, you've got a great playable club, and you can take a club like this Logitech and put it into the super game improvement category. Moment of inertia regarding putters is really important. It's more important by far than center of gravity, so it's just the opposite of iron and wood clubs that are coming into the ball and the ball's getting squished against them and there's a lot more force. On a putt there isn't very much force. But moment of inertia on off-center hit putts. So here I'm talking about all this heel and toe weighting in putters, and you're wondering, well, gee, they have high moment of inertia. What does that mean for me, the golfer? What it means is the longer a putt that a person hits, the farther they move the impact point along the club face. And generally it's in about an inch to an inch and a half an area, heel to toe. But it depends on the golfer's ability. Touring pros hit it on the same spot every time. No surprise, correct? So what we want to do is go with the highest moment, best heel and toe weighted putter, those are synonymous, that we can, so that we can hit the ball all over the face, but we still get the same force applied to the ball. So what it means is the ball will go the same distance, whether it's hit a half inch toward the toe or the center or the heel. They'll go the same distance. You'll get the same directional control out of all three because the putter won't twist. So very critical in putter design, and it's really nice to have it when you go for super game improvement irons, but absolutely a necessity in putter design. So that's our little talk on moment of inertia. I probably got going a little bit long on what I was trying to say, but I hope you have a very good feel for its importance and why I use this machine on every golf club I design. Okay, here's a little tip for you. Let me get this all set up. The ball centered on the putter, locking device, hit a putt. If you had hit literally thousands of balls like I've hit on this robot putting machine and tested all the different types of clubs on it, recorded and analyzed all the data, one thing's for certain, you would never, ever putt with a conventional wound ball. Well, we've talked about quite a bit so far regarding golf club design. How about if we take a break for a moment and go out and take a look at the machine shop, and in particular, let's look at the CNC mill, and I'll show you how that operates. Then after that, let's take a little tour of the grinding and finishing room to show you the various machines that we put different finishes on golf clubs. When we finish all that, we'll come back and we've got two short subjects left. One is C dimension and understanding how that brings together the items we've discussed so far and allows us to come up with a playability factor of golf clubs. And also I want to show you a little bit about how my putting robot works, because I found out some interesting results on that, and I'll share those with you. Okay, now we're out in the machine shop area. This is a Vectrax mill here to my right. It's a 3-axis CNC mill with a centroid control on it. I can basically control everything on it, and how it works is this way. When I finish writing the program back in the Golf Club Design Studio on the CAD-CAM system, I can then have it output code that this machine understands. I just save it to a floppy disk. I bring the floppy disk out here, shove it in the back of the machine, and then I can go ahead and graph on the screen the code that I just put in. This actually graphs it in 3-dimension or 2-dimension and shows me how the cutters are going to cut the parts, so I can be sure that it's compatible with the program that I brought in from the program that I had done in the studio on the CAD system. We also mentioned that I have a lot of tools pre-set up, and they're all set up on quick change holders. And what I have, and just to show you a few of them, we talked about engraving tools. Well, here's the engraving cutter. It's just a small pointed cutter for putting in face lines and any logos or lettering or numbers that we would like to put into the iron, the wood, the putter. I have hogging cutters that remove a lot of material fast. I've got the tapered cutters we talked about earlier that have slanted sides that go in and cut relief angles, whether it's for a release thing from a die or whatever you're doing, but I can, or it can be even a cosmetic look. So I have all these different tools along with, I mentioned earlier, digitizing. I've got collets for holding any particular drill, center drill, whatever you'd like to do. So this is kind of a fun thing for me. I enjoy being out here. I'm generally not dressed like this. I'm in blue jeans with my apron on and my modern machine shop hat. But I can sit here for 4 or 5 hours while this machine is running doing certain operations. And as I mentioned earlier, I've sat here for as long as a 9-hour cut. But what the machine does is it runs along, and it's not an automatic tool change machine. This is more of a tool maker's precision machine, if you will. So what it does is it mills along, and I've told it, say, what tool to start with. It stops whenever the next tool needs to be put in. I take out the tool, I put the new tool in that it tells me to put in, it runs again, then it stops when it needs another tool. Now, of course, I have predetermined all these tools by working in the CAD-CAM system back in the studio. So the machine is programmed beautifully to go ahead and build whatever prototype or master or whatever I happen to be doing at the time. We're now in the grinding and polishing room. I have all kinds of equipment in this room to put virtually any finish on a golf club. There's a vibratory in the corner back there, which I can run walnut shells in to vibrate and get a certain finish. I can put steel shot in it to get a different vibratory finish. And most people know that most ping golf clubs are a vibratory type finish, so that's what we're referring to when we mention that. There's stitched buffing wheels in here that have different compounds put on top of them so that I can grind a little bit on the irons and do some blending. As we all know, the blending part of a iron is very important in getting the look that you're trying to achieve. So when you're building the prototype, you certainly want them to copy that exactly into the master model, any blending or radiusing that you do. Behind me here up on the wall are a whole bunch of die grinders. And they're all high-speed, 25, 30,000 RPM die grinders with different carbide cutters in them, different grinding stones in them. And I use these to go down in and do any blending in a cavity that may need to be done. It's virtually impossible to get every little radius and nuance from the CNC mill transferred into an iron and have it perfect without having to touch it. I sometimes have to come in and do a little sanding on these wheels. I've got high-polished buffing wheels in here. I've got Beartex wheels that are flat Beartex wheels. I have Scotch-Brite wheels that are set up on a wavy washer, which is really great. If you're doing iron head refinishing and just cleaning them up, this Beartex setup on the wavy washers is excellent for putting on a good-looking finish, and depending on how hard you push, depends on how fine or how coarse the grain is. So we have a lot of other equipment in here. I've got sanding wheels that have rubber insides in them so you can get some blending there. And then outside this room, we have a full-size grinding and polishing lathe, which I also use to put on different finishes and do some serious grinding, because it has a 132-inch belt on it, and I have a lot more room for wear, and the belt lasts a lot longer than some of these shorter ones. Outside the room here, I also have a bead blasting setup. There's a sand blaster inside this room. So again, we can put all the different coarseness or fineness of blasting.